4. Proof. Let x1 belongs to n. Let x1 belongs to n. If a space n is generated by single element, if the space n is generated by single element x1, generated by single element x1, then result is posed. Then result is proved. Result is proved. Suppose x1 does not generate addition. Let x1 does not generate n. Does not generate n. Then by proportion x2, then by proposition, there is x2 with x2 with the norm x2 equal to 1. X2 with norm x2 equal to 1. And norm x2 equal to 1. Such that norm x2 minus x1 greater than half. ST means such that norm of x2 minus x1 is greater than half. If x1, x2 generate n, if x1 comma x2 generate n, then the result is 4. Then the result is 4. Suppose x1, x2 does not generate. This looks like a Berry's theorem in category real analysis. Suppose x1, x2. Let x1 comma x2 does not generate n. Does not generate n. Does not generate n. Then again proposition. Then again proposition. Again proposition. There is x3 in n. There is x3 in n. X3 in n. X3 in n. With the norm x3 equal to 1. with the norm x3 equal to 1, norm x3 equal to 1, such that x2 minus x3 greater than half. St means such that x2 minus x3, norm x2 minus x3 greater than half, and norm x1 minus x3 greater than half, norm x1 minus x3 greater than half, Continue this process. Continue this process. So this process must terminate a finite stage. Continue this process. This process must terminate. This process must terminate. Finite stage. Otherwise we do obtain a sequence. We would obtain a sequence of points on unit sphere, of points in a unit sphere which has no convergent subsequence, which has no convergence. CGT means convergence sequence, no convergence subsequence. Contrary assumption to that is a closed bounded set in compact. So then n is generated by x1 comma x2 comma etc. xn. Hence capital N is called. Capital N is called N is called capital N, finite dimensional finite dimensional N is called finite dimensional. So based upon this, we'll do one theorem, that is 4.3.6, important theorem. Any two n-dimensional Riemann space statement, any two NLS means normal linear space, normal linear, over the same scalar, field, are topologically or topologically. Topologically isomorphic. Isomorphic. Topologically isomorphic. Proof. Important theorem proof. It is sufficient to prove that n is n-dimensional. Any n-dimensional normal linear space. It is n of 2 pt means prove that n-dimensional normal linear space, n-dimensional normal NLS normal linear space over a scalar field F, over a scalar field F is topologically isomorphic to either real or complex. That means is topologically isomorphic to Fn, isomorphic to Fn, isomorphic to Fn with the norm, norm alpha equal to sigma r equal to 1 to n, mod alpha I whole square, whole power 1 by 2, alpha belongs to scalar field, nothing but alpha belongs to F of n. Next, let n be n-dimensional normal linear space. Let n be normal linear space. NLS means normal linear space over a field, over the scalar field, over the scalar field F, and suppose x1 comma x2 comma etc xn be a basis for n, be a basis for n, define t f power n tends to n as follows. So T of alpha equal to alpha 1 x1 plus alpha 2 x2 plus so on alpha n plus so on alpha n xn for alpha equal to, where alpha equal to is nothing but alpha 1 comma alpha 2 etc alpha n. X1 already we defined, x1 x2 xn, which belongs to scalar field, nothing but f of n means a scalar field. Right. From the definition, it follows that follows that follows that. F is 1 1 and on 2. Number one is F is 1 1. 1 dash 1 means 1 1 on 2. What is 1 1? So distinct elements capital A have the distinct images. Onto means the range should be equals to its domain. 1 1. 1 dash 1 means 1 1 mapping onto mapping onto. Now prove T and T inverse is continuous. Now we need to prove that T and T capital T and T inverse CTS means continuous. That implies T and T inverse BDD. BDD means bounded. Alpha belongs to F alpha already. So norm of T of alpha. Norm of T of alpha. Norm of T of alpha equal to norm of alpha 1 x1 plus alpha 2 x2 plus so r dash 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 plus alpha n xn. Less than or equal to, you have to separate. That is the less than or equal to. By the norm properties, what we need to do, alpha 1, alpha 2, alpha n are scalars. That means that one scalar, what we will write, what is the property for normal linear space? We need to write within the modulus symbol. Alpha 1, norm of x1 plus modulus of alpha 2, norm of x2 plus so on continuous. We need to write plus modulus of alpha n, norm of xn, norm of xn. Here norm of xn. And so we need to take alpha. Alpha is modulus, no? So alpha I is less than or equal to alpha I is less than or equal to mod alpha, norm of alpha for all I. For this condition, this implies norm of alpha outside bracket, norm of x1 plus norm of x2 plus so on plus norm of xn, norm of xn. Right here, this will denoted by norm of x1 plus norm of x2, norm of xn is denoted by capital M. Denoted by capital M. This is M denoted by. That implies then what we'll write? Norm of alpha into M, capital M, wherever M equal to, where capital M equal to what we are denoted, modulus of norm x1 plus norm of x2 plus so on plus plus norm of xn, norm of xn. Okay, xn. So same as m is finite, since m is capital M is finite. Capital M is finite. Capital M is finite. So norm of T alpha is less than or equal to capital M into capital M into norm of alpha, for alpha belongs to scalar, finite scalar f of n. So that implies T is bounded. PDD means bounded. Bounded. Here, no. Prove the T inverse is bounded. We need to prove that PT means prove that we need to prove that T inverse is bounded. T inverse is bounded. T inverse is bounded. Is to prove that implies is to prove that norm of T of alpha, norm of T of alpha is greater than or equal to small m of alpha. Alpha for all alpha belongs to f of n. F of n for some positive constant n. For some positive constant small m. So let capital A equal to x belongs to f of n. X belongs to f of n. X belongs to f of n. Norm of alpha equal to 1, such that norm of alpha equal to 1. Norm of alpha equal to 1. Norm of alpha equal to 1. So then it follows that A is compact. Since A is closed and bounded, it follows that A is compact. CPT means compact. Since A is closed and bounded. Since A is closed and BDD means bounded. Closed and bounded. So now consider M equal to small m equal to infimum. INF means infimum. Infimum. Norm of T alpha. Norm of T alpha such that alpha belongs to capital A. Alpha belongs to A. A is closed, it follows that A is closed. It follows that A is closed. It follows that small m is greater than 0 because we choose this is positive constant greater than 0. So norm of T of alpha is greater than m for all alpha belongs to A. Alpha belongs to A. So let beta belongs to Fn. Let beta belongs to Fn. F of n. And beta is not equal to 0. And beta is not equal to 0. Beta is not equal to 0. Put alpha equal to beta by norm beta. put alpha equal to beta divided by norm beta. Norm beta is greater than or equal to m. So therefore, norm of t beta greater than or equal to m of norm beta, then m of norm beta for all beta belongs to f of n. For all beta belongs to f of n. That implies T inverse is bounded. That implies T inverse is bounded. T inverse is bounded. This completes the proof of the theorem. Hence proved. Next. Definition. Definition 4.3.7 definition. 4.3.7 definition. Two norms, norm 1 and norm 2 on a linear space N. Two norms norm 1 comma norm 2 on linear space N. LS means linear space N, capital N. To be equivalent, if there exists a positive real, if there exists symbol, there exists positive real constant M, positive real constant M, positive real constant M, and small m and capital M, such that M norm 1 is less than or equal to capital M norm 2, capital M norm 2 for all small x belongs to capital M. X. In other words, two norms generate same topology on X. In other words, two norms generate the same topology. TO, PO, LO, GY. Same topology on capital X. So using definition, we will do one theorem, that is 4.4.2. 4.4.2 theorem. 4.4.2 theorem. 4.4.2 theorem. Let n and n dash be. Let n and n dash be. Let n and n dash let n and n dash be. Let n and n dash be. Normal linear space NLS means normal linear space over a scalar field F over over a scalar field F. Scalar field F. Scalar field F. Statement. Scalar field F. Scalar field F. A scalar field. N is a finite dimensional. Capital N is a finite dimensional. N is a finite dimensional. N is a finite dimensional. Then every linear transformation of n into n dash, then every LT means linear transformation of n into n dash, n into n dash is continuous or bounded. Is BDD means bounded or continuous. CTS means continuous. So we need to check proof of this theorem. Important proof. Let n be n-dimensional linear space. Let capital N be a, let n be a n-dimensional normal. NLS means normal linear space with norm. Let x1 comma x2 comma etc. xn be a basis for n. Be a basis for n. Basis for n. When each small x belongs, there exists a finite number of scalars for each small x belongs to capital X. There exists finite number of scalars. There exists finite number of scalars. Finite number of scalars such that alpha 1 comma alpha 2 comma etc. alpha n such that x equal to alpha 1 x1 plus alpha 2 x2 plus so on alpha n xn alpha n xn. Fine. Let norm1 let norm1 equal to sigma I equal to 1 to n alpha I equal to 1 to n 1 to n mod alpha I. It is easy to verify that norm1 is on n. Norm1 is on n. N means normal linear space. By definition, norm1, norm2 are equivalent. Just now we discussed definition. No? So by definition, norm1 comma norm2 are equivalent. Norm1 and norm2 are equivalent. Norm1 and norm2. There exists a positive real constant. There exists a positive real constant, capital M, real constant, capital M, such that norm x1 less than or equal to m norm of x. For all x belongs to n. X belongs to n. So T is linear transformation from n to n. Let T is linear. LT means linear transformation from n to n dash in transformation n to n dash. Yeah. For all x belongs to capital N. So norm of T of x equal to norm of T of sigma I equal to 1 to n alpha I xi. Sigma I equal to 1 to n alpha I xi. Alpha I xi. That equal to norm of sigma I equal to 1 to n. Alpha I T xi. Alpha I T of xi. Alpha I of T of xi. That means is less than or equal to inequality is less than or equal to sigma I equal to 1 to n mod alpha I into norm of T xi. Now is less than or equal to norm of x1 maximum of T of norm T of x1 norm T of x1 comma norm T of x2 comma so on norm t of x n, norm t of x n, norm t of x n, that equal to k of norm of x, k of norm of x, of norm of x, where k equal to 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 maximum capital M, capital M, maximum of norm of tx1, norm of tx1, comma norm of tx2, comma etc. Norm of txn, norm of txn, norm of txn. Therefore, norm of tx, norm of tx less than or equal to k of norm of x, k of norm of x for all x belongs to n, x belongs. That implies t is bounded. That implies t is bounded. T is bounded. Hence continuous. Hence CTS means continuous. This completes the proof. Hence proof. So today what we discussed, two definitions. Means first one is definition cum theorem, and theorem, two theorems, important theorems in fourth unit. Okay, if you see these important one will come there, right? Next we will discuss dual Banach species. Next class we will discuss dual Banach species. Any doubts? Okay. Tomorrow, sharp 10:30, we'll discuss fifth unit. Try to finish 6:30. Two important units. Okay. We are from Gundit Satish. So I'm leaving the meeting. We'll meet tomorrow 10:30. Thank you.